Hi everyone, and once again, welcome back to the introductory course on Database Management Systems and SQL. So today is the 8th module where we'll be looking into some more advanced concepts, including something in the queries and also some aspects of the physical design, right? Going ahead, just to a reminder, like this course is being brought to you by the Launchpad initiative of Newton School. The link to Newton School will be given in the description section of the video, so please feel free to check that out. The course that you are seeing now, you can view those lectures on YouTube for free, or you can register for the course from Newton School's website as well. For registering, go to Newton School's website, either log in or sign up based on whether you're a new user or whether you're a returning user. After you have successfully logged in, you will be redirected to the dashboard of Newton School. There, search for the course, the complete database management system and SQL under the Launchpad section. Here you can click on apply once you find that particular course. And once you have applied, you will be asked for some details, and then you can see the course appearing under your tracks. The advantage that you get by registering for the course from Newton School site is that along with the video lectures, you also get to do assignments, daily quizzes, and there will be a discussion forum for doubts as well. And if you have completed the course, then you will be eligible for getting a certificate. All right. So we will go ahead with today's course. So today's concept is, first we'll be looking into groups. So groups are something that is a special way of SQL queries. So when you're writing SQL queries, grouping is a way of how you can group multiple rows that you have based on some sort of attributes. And after you've grouped them, you can do some aggregate functions on them. And then we'll be looking into indexing and hashing. So that is some of the physical design aspect of the database. So first we will be looking into groups, and then we'll go into the next part of it. So what groups, as I said, what they do is that based on whatever you're writing in the from and the where clause of your query, whatever filtered records that you have got, you can actually now group those queries into multiple tables or into multiple sets. So when you're writing a simple select from where, all that you're getting is you're actually getting just a row of records. You're just getting multiple rows, right? That you're getting multiple records, and then those records are coming up some order. Like let's say if you're given an order by query, or if you're not given an order by query, then you're going to get the default order by mechanism of SQL, and you're just going to be getting back those records. Those records will be like raw records to you. What group by does is it takes those records and groups them by certain attributes. So let's say I've said that, hey, I want to get all the students and I want to group them by the department IDs. So it is going to take those records that you have got. It is going to sort it, or it is going to put this bunch of records into different buckets, which each bucket belonging to a different a type of department. So this is what grouping actually does. And once this grouping has been done, if you want to apply some aggregate function, like let's say you want to apply the average function or the maximum function, minimum function, whatever it is that you want to apply, you can apply those functions into those individual buckets. And the result that you now get is the result you're going to get for each group, you're going to get one result. Earlier, what was happening was when you were doing a group by function, it was grouping on, or rather, when you're doing the aggregate functions like average, maximum, or anything, it was doing that aggregation on all the records that you had. But with group by, what it is doing is, what it will be doing is, it is first going to take the records, put them into multiple buckets, and then into each bucket, it is going to be applying those operations. So if you want to visualize that, if you want to visualize that from a table, so assume that you have this student table which contains student name, CGPA, and the departments that each of the students belong to. Now let's say you are putting a group by clause on top of this row of records, and you are saying group by department. So what is going to happen is it is going to take this table and it is going to split it into two, and it is not going to split it vertically, it is going to split it horizontally. That is, it is going to, if you're saying group by department, then it is going to take all those students which belongs to the same department and create multiple clusters or multiple buckets out of it. Like for example, here you can see you have got two students, Manju Verma and Akhil Verma, who belongs to the MME department. So when I'm saying group by department, it is keeping the same attributes. All the attributes are remaining the same. It is just that all the attributes in each of this bucket is now going to have the same department. Similarly, since there are two distinct departments in this particular table, it has created two buckets. Have there been a third or a fourth department in this table, then it would have created three buckets or four buckets, as many number of unique departments are there. So based on whatever you're grouping it by, it is going to it is going to see how many unique number of records you have for that particular attribute. And then for each attribute, it is going to keep all the records into a single table. So this is what exactly group by does. So we will go ahead and look into some of the practicalities of it. So we will start with the queries that we finished off last finished last time. So this is again, I'm running this queries, everything on Newton School's IDE. So if you know, the Newton School has got a playground option using which you can actually write your code and keep all your code in same place. You can write code in C#, Java, or in whatever other programming languages that is supported here. So here I'm writing it in SQL. And to give everyone a refresher of what exactly our data structure looks like, it has a department table which contains the department information, a student table which contains the information for a student like roll number, name, marks, age, and everything. And this student table has got a reference to the department table via the department ID foreign key. There are two other tables. One is the course table, which contains the courses that each student has undertaken. This course table also has got a reference to the department table, the business logic being that every course is being offered by a particular department. So you need to have the department reference here in the course table as well. And there is another bridge table. So a bridge table is something which we use when you have an M2N or many-to-many relationship. So since one student can take many courses and one course can be taken up by multiple students, the student to course relationship is what we call typically a many-to-many relationship. And hence to represent or to create a reference between two tables which have a many-to-many relationship, we are creating a bridge table called student course, which is containing the student roll number and the course ID. Student roll number references the student table, course ID references the course table. So it has got two foreign keys here. Now let us first start with a simple query. Like let's say I'm going to be using the student here. I simply want to calculate the students. I want to calculate the average of all the students that it is CGPA of all the students. So we already did something like this in the last video where we saw all that we are doing is we are taking an average of the given attribute, and from all the rows that it has got, it is going to create the average and it is going to give you back. So that is exactly what it did here. Now, one thing is when you're doing aggregate, you can actually do aggregate on multiple tables, right? Like for example, right now I'm doing it only on student table. So let me just make a start. What if I want to do it on both the student and the department table? It is possible to do that. So let's just join two tables first. So if I want to obviously do some operation on two tables, I need to first join them. So let me say on student dot department ID is equal to d.dept ID. If I just go ahead and do that, what I get is I get both the tables and data from both the tables, and they are joined via the department ID. That is, the student table has got a department ID, which is actually a foreign key reference to the department ID, dept ID of department table. So using that, I join them. Now here also I can do an average, right? I can do an average of, let's say, S of CGPA. So let's go ahead and do that. Here I'm still getting the same result because see, the number of students hasn't increased or decreased, right? It is only that now on the table which I'm trying to do the aggregate, it has got a lot more attributes. But the values and the CGPA that each and every student has received, that really doesn't change. So if I can go ahead, okay, I shouldn't have pressed that. Sorry, my bad. I pressed F5 by mistake. Yeah, if I go ahead and run this once more, yeah. Yeah, I'm still getting 8.21, right? I'm not getting anything else here because it was all that is happening is that earlier I was getting only the student table. So I was getting only this, the first 4 or 5 columns, and now I'm getting other columns which are getting attributed towards it. Anyway, now what we'll be doing here is now we'll be trying to do a group by, and after we do a group by, we'll be trying to do some aggregate operation on it. So one thing that we can group by really well here is on the department. So let's say the query says that I want to see the average marks, not only of the entire table, but I want to see the average CGPA in each department. See, because getting the entire average of a particular university doesn't really make sense, right? Because every department has its own marking ideology, and so that's the reason why a lot of these universities has relative marking mechanism, right? But anyway, so the concept here is that I'm saying that I need to for each and every subject that I have, each and every course that I'm offering, for each course I want to see what is the average that I'm getting, average marks that I'm getting. So this is again a very good use case for a group by scenario, because we know group by what it is doing is it is going to take this record and it is simply going to put it into multiple buckets. Like it's going to put MME students in one bucket, CSE in one bucket, BT in one bucket, and stuff like that. So let us do that first. Let us first write a group by. So I'll say group by. Now I want to group by the department, but I can do the group by department ID as well. or I can do it by the department code as well. Now, see, both if I do, I say, let's say S by department ID, this will give me the same result if I do d.dep code, because at the end of the day, department ID and department code, they are actually kind of meaning to the same thing. But the reason why it is better to do it on the department code is because, see, when users are concerned, that is when users are concerned in the sense like when you have actually when a user actually enters that, hey, you know what, I want to see the department, I want to group by a particular department or anything like that, your users will not know what a department ID is, because department ID is just a number which is a very database concept, that is you have created of something like a numeric integer to represent each and every department. That's the reason why department ID is something which is known to you as a developer. But when some business users comes into the picture, they don't know what a department ID is. What is 1, 2, 3, 4? They don't know that. They know the code of a department. Like computer science and engineering is CSE, metallurgy is MEB, mechanical is MECH, or whatever, stuff like that. So that's the reason why if you're trying to do a group by and you have got some users out there, it is better to do it on a department code, which is actually easier for everyone to understand. However, you can always do it on department ID also. It's going to give you the same result at the end of the day. So I've done the group by now. Now let me just try to do an average. So now what do you think is actually going to happen? Now, as we know what group by does, group by is done into different buckets. And now if I'm trying to apply an aggregate, it is going to do that function in each and every bucket. So how many departments do we have? First, let us see that. I've got MME, CSE, biotechnology, mechanical. So I have actually only 4 departments here, 4 unique departments that are present here. So if I go ahead and run this, so it should do the average in all the 4 departments, and if it does average in all the 4 departments, I will get 4 results. Yeah, that's good. But you see, there's a problem here, and the problem here is that I don't know, hey, what are the attributes here? Like, hey, what are the, like, for which department is it? That I don't know, right? For that, let me just go back to the slide for a moment. So see, one thing you can see here is that when you have done a group by on a particular attribute, that attribute remains common in all the buckets, right? Like if you have done a group by department code, then the department code remains common in all the buckets. So the attribute on which you have done the department, on which you have done the grouping, that attribute remains common for all the aggregate, even when you're doing an aggregate function. That means what it is happening, it is looking into all the CGPAs which are present in this particular bucket, and it is doing some calculation, returning back the result for you. But no matter which row you take, you see all the rows have got the same department. It has got the same department code. So I can print the department code along with the average, and it should print me, okay, which department it belongs to. Because if I write here something like, let's say average this, and I write something like d.dep code, see what it is going to do is for each bucket, it is going to do a CGPA, and it is going to find out, okay, what is the first department code which is present in that particular is present in that particular in that bucket, and let me just print that. So let's go ahead and do it. There it is. I get the department name now, and that which department has got which department has received which category. But now here, if I try to do, let's say c.student name, now this is where the query is going to get funny, and it's going to give you weird results. In some situations, it might even give you an error. See, here it is giving some names, but this names actually doesn't matter. Or rather, what it is doing here is, see, when you have done some sort of aggregation, like average, count, max, or something like that, you are literally collapsing multiple rows into a single row, right? So now since you collapsed all these records into a single row, and you are telling SQL, hey, give me the student name, it doesn't know which name to give you. It just gives you whatever student name pops up at the first record probably. So it depends on the kind of version of SQL you're using and what kind of vendor you're using. Like maybe in Microsoft SQL Server, you may get a different behavior. Oracle, you may get a different behavior. In SQLite, you're getting a different behavior. That's why s.student name really doesn't make any sense here. But however, when you do d.department code, all the department codes are same, right? Since all the department codes are same, that is the reason why it doesn't matter which department codes it picks up. It picks up the first department code or the last department code. It is always going to pick up the same value, because you have already grouped all this by the particular department, and each bucket contains the same department code. So here, so let me keep that as the department code only. Let me go ahead and trigger that. And there it is. You get the value. Now, what if I want to, instead of max, you can, if you want to do average, you want to do max. That is, I want to know what is the maximum CGPA that each department is receiving. There it is. Biotechnology is 9.24, CSE is 9.48, mechanical 8.6, and MME 9.1. So, so the max functions are also working fine. So similarly, You can do you can do any type of aggregate functions here. Now let us try to increase the scope a little bit, and what we're going to be doing is, see, when I'm doing a select and from here, I have selected all the rows because I'm just doing a from, right? Now there can be a situation where I do need to select all the rows. It's a group by operation that I'm doing. I need to do a group by operation only on a subset of the rows, not on the entire table. It's possible. Like for example, let's say now the query that we are looking for is, hey, I want to know the maximum CGPA for each department for female students. That is, I want to know that for each student, what for each department, what is the maximum number that the girl students have received. Now, for that, you cannot use this particular query now. The reason why you cannot use this particular query is because here, when you're selecting the records or when you're doing the aggregate function on each bucket, each bucket contains records for both male students as well as female students. That is, if I just remove this part for a moment, if I just forget about the group by and everything, see, let's start from student. This query is pulling up rows from all the entire student table, which contains male students as well as female students. But here my query specifically says that I want to figure out the marks only for the female students, that whatever aggregation I'm doing, whatever grouping I'm doing, doesn't matter. I'm doing it only for the female students. That's it. So if you are trying to do that, let's say if you are doing something like that. So all that we need, so what we need to do here is, when I am pulling the records and before I can do aggregation or grouping on them, I need to filter out the male students, or I just need to select only the female students. And what is the way to do that? Where, so I say where s dot gender is equal to f. Now let me bring back everything. Select max CGPA, and here I'm going to be giving let's say the D dot department code. That's it. Looking well. Let me go ahead and run this function. There I get it. So here the records have changed a little bit, and we would try to do some manual verifications. For mechanical, it is saying the answer is 7.9. So let us go into the students, and we will see that that for the mechanical department, we have got one student named as Christine D'Souza, female. The value is 7.9. But for no other students, so mechanical is department number 4. So you have got department number 4 as Anuj Tyagi. Again, that's male, so that value is not calculated. You have got Pragati Singh, female, value is 7.4, and you have got Christine D'Souza with 7.9. So obviously the competition is between Christine D'Souza and Pragati Singh. One is 7.4, another is 7.9. So that's a reason 7.9 wins, and so 7.9 has been printed. Although the maximum is actually Anuj Tyagi, but since Anuj Tyagi's gender did not match, that's the reason why when we're doing the where, we already eliminated that data. So this is how we can actually use the where out here. Now let us try to look into something a little more interesting, or a little more interesting here, where I'm going to be saying, okay, I need to know all those departments, or okay, let me just write an average here probably. It's the same thing, but I just want to see the average because so that I can see what kind of data that we have here. So here it is. So let's say now I am saying that, hey, I want a query, or rather I want to know all those departments and their average CGPA, where the average CGPA of female student is at least 8.5. So two where statements or two filtering has happened here. The first filtering it is saying is that I want to get to, so let me say the query once more, and then it probably might be easier. I want to know the departments and their average CGPA in which average CGPA of female students is greater than 8.5. That is, female students average is at least 8.5. I want to know the details of all those departments. Yeah, so the question is, how do we do that? Now here you see there are two kinds of filtering that is happening. One filtering is happening before the aggregate, another filtering is happening after the aggregate. Like before even I can do the aggregate, I'm telling you there is a filter which says that I want all the marks for the female students. That means before you can get the data on which you need to apply the aggregate, you need to apply the where statement to filter out all the male students, to eliminate all the male students and select only the female students. That's the first level of querying that you have already done. That's the first level of filtering that you have already done. That is, you are only selecting the female students. Now the next level of querying that you need to do is, that is, you now need to select only those records where the average is greater than 8.5. So this is where it becomes a little tricky. See, yours from and where, this was being applied even before aggregation could have taken place, right? That is, you're applying a where on the data that what so in the from you have kind of actually mentioned that which are the tables you need to target and how you need to target the tables. That is this inner join, outer join, or whatever you're trying to do. And after that is done, you are actually filtering those records out of the table. So you've got the female records. You have got only those students who are whose gender is F. Now it is saying that you also need to filter out those records for the average is greater than 8.5. Now, how do I do that? Because the problem is in where I cannot do it anymore, right? Because when I'm applying where, aggregation hasn't happened yet. Aggregation only happened after the where statement is executed and I get to know, okay, who are the female students that you have. Aggregation is yet to happen. After aggregation has happened, then I'm saying now you need to apply another filter. So for this, we will be introduced to another clause which is known as having. So having and where, they are both almost similar, but the only difference is the having clause applies filter after the aggregation is over, and where clause applies filter before aggregation can be done. Before you can select which of the rows I want to aggregate on, that is where statement comes into the picture. And having statement comes into the picture when aggregation is already over and now you want to do some filtering based on the aggregated results. So now here I have to say where average CGPA is greater than 8.5, greater than equal to 8.5. Now if I go ahead and run this query, there it is. It's only biotechnology and ABM. And the reason why it became only biotechnology and ABM because the other ones that we had, let us just without average also let me run the query once more. So you have got the other two departments, which is CAC and mechanical. Here the average marks for the female students were less than 8.5. So that's why if I do an average, having average greater than equal to 8.5, I've got only the first record and the last record available with me. So if I go ahead and run that, yep, there you go. That is exactly what we actually wanted. All right. I'll just take a look into the live chat to see if there are any questions on the group by queries. If not, we will do one more interesting case and then we'll move into the physical design aspects. Okay. No questions. All right. Just a quick reminder that if you do have any questions, please put them in the live chat if you're watching the course live. In case you're not watching the course live, you can either post your questions on the comment sections, or you can go ahead or if you're registered for the course from Newton School's website, you can go to the discussion forum and you can post your questions there. Someone will get back to you with your notes. All right. Good and fine. Now we will be doing something a little interesting. What we'll be doing something interesting is that we'll be doing group by only, but we will be making it a little more robust. That is, or rather, we'll be making it a little more complicated. So for that, we'll be making a simple change to our database actually. So currently in our database table structures, we have got the course, but we don't have one thing. That is, we don't have the credits. Credits means that is okay. So in any university, any college that you go, every course has got certain credits. Like if you have taken a very complicated course, it has got a very high credit, like credit 5 or 6 or something like that. However, if you've taken a very easy course and that course is not very optional, it's an optional course for you, then you get a low credits for that, like credit 3 and everything. And then there are many multiple rules and business rules which says, like a lot of universities has rules which says that every semester you need to take minimum of that just 15 credits or 20 credits of worth of courses. And if you want to get a certificate, then you need to finish at least 60 credits before you can leave the college. Only then we'll be giving you the degree certificate. So these are all this, we have this complicated rules that is available in a lot of these colleges and universities. So let us try to account for them now. So let's insert something called credits here. So credit, again, it's going to be an integer value. Sorry, credits again is going to be an integer value. That's it. And let's make it as not null. Fine. And now when I'm entering the data, I just need to insert the credits properly. So let's say after course name, I am saying credits. I need to do that for all of my statements here. A bit of a tedious task here, but okay, all right. And then I need to enter the credit. So let's say database management system has got a credit of 5. Object-oriented programming has got a credit of 3. Let's say Steam Engine has a credit of 4. Alloys has a credit of, let's say, 3. Again, these are all random values. It doesn't mean anything. So I'm just putting values as and what I see fit. All right, I've got the credits and everything. Let us go ahead and try to do a join here. So remember, if you do remember the join, here we need to join on 3 things actually. Now let me join the select start from students. Let's call it as S. So I'll be first doing an inner join with student course table. S dot sorry, S dot roll number is equal to SC. So student course will call it as SC. SC dot student role. Again, this one is going to have another inner join, and this one will be joining with the course table. So course C on again SC dot course ID is equal to C dot course ID. Let me just do the student dot role S dot student name C dot course name and I just C dot credits. Let me go ahead and trigger this. So it's a 3-way join that we have done. Okay, this is taking some time. Probably let's open up in a new window and try it once more. This thing, maybe it got stuck somewhere. Copy this, close this, open my playground. Probably create a new playground this time. Oops. Oops, all right. I'm gonna go ahead and paste the whole thing and let's run it this time. Hopefully, yeah. Oh, sorry, I did not select the language. SQL, right? Yeah. All right. I think there was an issue with the earlier window. Something got frozen. All right. So here it is. I'm seeing now the student and the course that the student has taken, and I'm seeing that okay, what is the course credit that each student has taken? All right. Now let's try to do some aggregation here. So the first aggregation that we are going to be doing here is, let's say I'm saying that hey, for each student, tell me how many courses each student has taken. Now, when you're doing an aggregation and you have been asked that how many, or that means you are actually going to count the number of rows that you have there, right? Average, max, minimum. Average was actually doing an average of a particular value. Max was taking the maximum. Min was taking the minimum, and then the other things like standard deviation, everything is there. But count is an aggregate function which simply counts the number of records that you have, and it counts the number of records that you have, and it gives you a result for that. So here we have to do a count, that is for sure. But if I read the query back again, the query says that, hey, I want to know how many subject has each student undertaken. So if I just do a count, it is just going to give me count of the total number of records that you have. Like for example, if I do a count here on this particular, in this inner join, it is going to see okay, how many students are there, how many subject each student has taken, plus, like this way. But here I'm saying, okay, I don't want to know the count for all the total number of student and courses combination that you have. Rather, I want to know for each student how many courses are there. So this is again a very classic case of group by here, because what I'm saying is that I need to get the result of count, but I need to group it by the students for each student. So if I do a group by let's say the student roll number, I'm going to get like, let's say the buckets, I'm going to make it. So how many students are there? Let's say I've got around, I guess, 1, 2, 3, 4. I guess I've got 4 students marked here. So I've got 4 students here. So I'm going to be taking it into 4 buckets. And then for each bucket, I'm going to count how many records are there in each bucket. So let's do a group by, and I'll say a group by S roll number. And after I've done, I'll be doing, let's say, a count on star. Count on star means that I'm just counting all the rows that you have. If I don't give count star, I can give count of a particular attribute name as well. Then what is going to do is it is just going to go into that attribute and see how many unique values of that attributes are present. But here, all I need to do is how many rows are present. So I'm just doing a simple count star. So let me do a count star and just trigger this. There it is. So I've got Manju Verma taking 4 courses, Pratik Bhattacharya has taken 3, Ria has taken 2, Anuj has taken 4. And just to ensure that we are doing the right thing here, let me just remove the count and we'll just do c.course code once more, and I'll apply this. So I've got, let's see, so Manju Verma, okay, sorry, I've done a group by first. So let me remove the group by here. So here we can see, so Manju Verma has taken MCB, ST, ALL, and OOP. So actually 1, 2, 3, 4. So there are 4 courses in the name of Manju Verma. In name of Pratik B, there are 1, 2, 3 courses. So Manju Verma has 4 courses and Pratik B has 3 courses. Now let me again go ahead and do the group by. Group by is the roll number, and here I'm going to be doing, let's say, all star. That's all. Nothing else is needed. Go ahead and execute this. So yeah, Manju Verma should get 4 courses, Pradeep should get 3 courses. Meanwhile, we have got Riya Mishra and Anush Tyagi. They have also got, let's say, 4 courses. All right, good and fine. Now, let us do one more query, and this is going to be a bit more complicated than this. So here, let's say we are saying that, okay, there is a particular rule in the university which says that every student must either undertake 3 courses or they must have a credit of 15. That is the total number of courses they have taken, that must add up to 50. So all the credits that they have taken. If you have not done that, that means you have taken insufficient number of courses. You still need to take more courses, or you need to change your course to take a higher credit course. A lot of universities actually has this rule. This is not a made up thing. There's a lot of universities who actually give you this rule that you need to take either 4 subjects or you need, or your total credit, or you need to take at least 20 credit subjects. So when you're doing that, now there are 2 things which are coming into picture. The first thing that is coming into picture is the number of courses which you have taken, which you already saw, which was count star. Now the thing is, you have also been given, you need to figure out, okay, what is the total number of or total credit that you have taken. So which aggregate function do you think that makes sense here? See, average, maximum, minimum doesn't make sense, because average is going to average the total number of credits that you have. Max is going to give you the maximum number of credit, maximum credit course that you have. Min is going to give you the minimum the subject with the minimum credit. But here I want to sum up all the queries, sum up all the credits for each and every course and give you back that result. So the aggregate function for that is called sum. So sum, I'm going to be doing it on, let's say, the course, on credits. All right, C dot credits. Go ahead and let me execute that. And there you go. So there we have it. So we have got Manju Verma who has taken a grade of 14. Pratik B has 11. Riya Mishra has 9. And Mr. has 15. Now, here what we need to do is, I have also told you that I want to find out all those students who has taken at least 4 subjects or has taken a credit of 15 minimum. So for that, now here we have to again use the having clause here, because I am trying to do some query, or I'm trying to do some filtering on the aggregated result. Like aggregation, like count, sum, these are all the aggregation results, right? I want to do some querying or filtering on this aggregation results. Since I want to do them on the aggregation result, I cannot use a where clause here, because where clause is used before aggregation. So here I need to use having. So having, the thing is, our theory is that having count at least 4. So at least you have taken 4 subject, or your credit. So your credit is sum C dot credits again, is again at least 15. So here, if we just see the result here, we can see, so we have got Pratik B and Riya Mishra. These are the 2 students who are actually validated, because Pratik B has taken only 3 courses and Riya Mishra has taken only 2 courses, and both of them have got a credit of less than 15. So ideally, if I go ahead and trigger this, all the students except these 2 students will come back. So if I go it, so here it is, Manju Verma and Anush Tyagi. So they have taken a sufficient number of courses here. So this is how you can actually do complications in aggregations. Now, like you know, in real world, the queries can get even more complicated than this, but this should give you a starting idea as to when you are trying to, you know, like buy a certain thing, or like if you have been given queries where you have to say, I need you to group it by a certain things, or I need to get the results for each department, for each classes and stuff like that. This is a way to do it. Grouping. So group by is actually one of the more advanced concepts in SQL queries, and there can be, again, as I said, multiple complications that can arise out of it. But group by, having, where, so this should give you some basic ideas as to how you should approach problems. Okay, before I go into the physical design portion, I would again like to go ahead and see whether there are any questions posted. Okay, I do not see any questions posted. All right, fine, no worries. So I will then go ahead with the remaining section of the subject today. So now we will be jumping a little bit back into theory, but again, this is also very important theory. So now we'll be looking into the physical design aspect. So when you are designing a database, and we saw that in the previous video, also in the second module of this series, about the database design process. That is, so initially you need to find out the analysis. That is, you need to talk to your business experts, your program managers, your solution managers, and you need to understand what is the system that you are building. What are the domain rules that are applicable to this particular system? Then after you have understood what are the systems and what are the entities which are involved, you need to create a conceptual model of what are the entities that are present, how those entities are related with each other, how many types of, what are the attributes that each entity has, and stuff like that. That's a conceptual model. After you have created the conceptual model, based on the complexities that you have in the conceptual model, you need to choose a physical model, or rather you need to choose a logical model. So in the logical model step, you need to choose whether you want to use a relational database, you want to use a NoSQL database, you want to use a graph database, or stuff like that, based on how your entities are spread across. So let's say now for the interest in this course, let's say you have chosen a relational database management system. So if you have chosen a relational database management system, then you need to convert your ER model, which is a conceptual model, into a logical model, where you're going to be defining what are the relations you have. Relations are nothing but tables. Then how these tables are related with each other, what are the foreign keys, what are the primary keys of the tables, and stuff like that. Once that is done, you need to define the schema to ensure that you do not have any duplicates. That is, when data is inserted into a schema, you need to ensure that there is less number of duplicates and less number of inconsistency, thereby so that you can reduce the number of anomalies that can happen when you're operating on that kind of data. So that is a schema definement process where we can do things like normalization and decomposition, which we saw in the previous video. Now, the last aspect of the database design is the physical aspect of it. That is, you know how the schema will look like, how the data will be stored, and everything. Now, the question is, how are you actually going to store the data in the physical hard disk? See, at the end of the day, your data needs to be stored in some physical server, right? This data is nothing like it is not in the air or something like that. It is something which needs to be stored in some sort of a physical server. So you've got a server, and in that particular server, you have got a hard disk, and you need to store this data in that hard disk. Or you can even multiple servers, and the data can be distributed in all these servers. Because if you're creating a huge database which contains, it's a terabytes and petabytes of data, it is impossible to have one single hard disk, have all the data. So you need to take the data, partition the data, and push it into multiple hard disks and stuff like that. So database, so in physical design is all about this particular aspect, where you now need to figure out what is the best way to store the data so that you can speed up the queries, so that you can scale up the database properly. Even when new data comes up, you need to ensure that your database can scale easily. So do you want horizontal scaling? Do you want vertical scaling? Or what kind of file system do you want to store the data in? Like, do you want to use a FAT32 file system, or do you want to use something else? How can you compress the data? How can you improve the query speed of the data? By ensuring that when you are storing the data in physical memory, you are storing it with certain other attributes, or storing it properly, partitioning it properly, to ensure that when someone is trying to get the data, when they're trying to query the data, your access speed is maximized. So we will not basically be looking into each and every aspect of the physical design, like partitioning, sharding, file system, compression, and everything. We will basically be interested in knowing how do we increase the query speed, because that is what is really, one of the most important aspect of it. That is, when you are actually looking into the data, that is, let's say you've got terabytes of data, and you have done a schema in such a way that is, you have made it into such fine and granular tables that there will never be any dependent duplications or redundancies and stuff like that. However, at the end of the day, someone is using your database to read information. But they're obviously using it to store information as well, but they're also using it to read information, understand what data has been stored, and based on the data, take some action. So you need to ensure, so one of the most important aspects is that when you're storing the data in your physical memory, you need to ensure you store the data properly, so that when queries are triggered, when someone is querying for the data, that query latency is minimized. Okay. So some of the mechanisms of using how you can actually increase the query speed is, first one mechanism is hashing. So hashing, once again, like people who have some programming or some background on data structures and algorithm, you can always relate it back to something like the hash table that you have in Java. So, or you have got something like sets also that is present in C. If you're from a C# background, you have got dictionary, which all uses the concept of hashing behind the screen. So what hashing basically does is, or what hashing is that you take an attribute, like whichever attribute you want to search on. Like, let's say in the student table, you want to search on the student name, let's say. So you take the student name attribute and you hash it, and you keep it in a different location. You keep it, let's say, let us look into a very simple example initially. Let us think that everything is in memory. So let's say you're using something like a hash table. Like a hash table that you have in Java, let's assume that you're using something like a hash table where you are actually storing all the student names. And then from the student names, you're putting a pointer back to the student's actual record. So that is how. So that is basically how actually hashing works, right? You take a value, those values you want to which you want to search by, create a hash of each and every value, and then you store that hash in a different hash table. And from the hash table, you keep a pointer back to the original record. So what is the advantage that you get by doing this? So hash table is really fast, and it can achieve a complexity as low as O of 1 in multiple cases. And average cases, it might go up to log n also if there are too much of collisions that is happening. Again, for the interest of this course, we will not be delving very deep into how exactly hash table works. Interested viewers, you can go ahead and take a look into how exactly hashing works. But basically the idea is that when you're storing information in a hash table, you can retrieve information extremely fast in O of 1 in some of the cases. So let's say if you're searching for a student by its student name, let me go and probably go to an example. Let's go to this example only, or maybe I'll go to this example. Let's say these are the student names that you have. And in this student, I'm searching by, let's say, Pratik Bhattacharya or by Riya Mishra. So what if I do not have any hashing or any mechanism is your SQL needs to come to this table, search each and every record that you have, and then search, okay, where is Riya Mishra or where is Pratik Bhattacharya? And in case this table is huge, there is terabytes of data, that is like millions and millions of students' information you have kept here. Then depending on the total number of records that you have, it has to go and search each and every record. That is the name Pratik Bhattacharya, is the name Pratik Bhattacharya here. So that's going to be a problem. Instead, what if I create a hash table? And in a hash table, I search and I keep Pratik Bhattacharya and I point Pratik Bhattacharya to the exact record where Pratik Bhattacharya is stored. That is exact block address. By block address, I mean, so your data is at the end of the day stored in a hard disk, right? In hard disk, it is divided into sectors and blocks. So each block can store one or multiple records. So if in a different file, I keep the hashed value of Pratik Bhattacharya and I point that value to the exact record or to the exact block where Pratik Bhattacharya's entire data is stored, then when someone is searching by Pratik Bhattacharya, all I need to do is search in the hash table, which is very fast, as we discussed. It is very fast compared to searching in the disk for the entire table. It is very fast. So you search in the hash table, you figure out, okay, this is Pratik Bhattacharya. You go to the pointer, you follow the pointer, come to the original table, and you get the results. That is how fast it is. You do not need to search the entire table. So something which was probably going to be O of big N might be solved in O of big of 1. So this is how you increase the speed by actually using a hash table. Let us look into some example or rather some process. So when you're actually inserting the data into the means, let's say you have said that I'm going to be using hashing to speed up my query. So what happens when you're inserting the data? First, you need to calculate the hash key, then keep the hash value in a hash table. Along with the hash value, we need to add a pointer to the actual physical memory where the data record is stored. And then in case you have collision, you can use something like open addressing and chaining. I'm not going into deep into what is open addressing and chaining. People who are interested, I've given you the terms. You can go ahead and search for it. And when you're retrieving a value, again, the same thing. Let's say you're searching by the name. So first generate the hash key of the name, then search the hash table for the hash table for that hashed value, which will be very fast because it can be O of 1. Hash tables are very fast. And once you found the value from the hash table, see the pointer which is stored along with it, go and get the data. Let us look at a perfect example. So let's assume that here I am, sorry. Let's assume here I'm hashing based on the roll numbers. Like let's say I'm saying that, hey, I need to search by the roll number. So that's the reason I'm hashing the roll numbers and giving it in a particular hash table. And this is the original table that you have. And the hash function that I've used is it's a roll mod 3. Now there can be, ideally you are not going to be using something as simple as this. If you're using internal hashing or in-memory hashing, you will be using something as simple as the, otherwise your hashing function might be a little more complicated. Now, what is a good hashing function and everything? Again, interested people can go ahead and read about it, like what is a good way to hash and everything. Anyway, so let's say if you use something like this roll mod 3, then first the roll number is 71, right? So 71 mod 3, the answer is 1. So when you've got a hash table, so in the hash value 1 is going to be pointing to the first record. Similarly, the second record is 47. 47 mod 3 is going to be 2. So in the hash table at value 2, position 2, you're going to be keeping a pointer to the second record. Then you have a Riya Mishra whose roll number is 33, whose value is actually 0. So in the hash table from the 0th position, you'll be keeping a pointer here. Now for roll number 59, there is going to be an issue. The issue is going to be roll number 59, hash value is also 1. So when the hash value of hash value is 2. Now when the hash value of 59 is 2, In 2, I have already stored a pointer to 47. Now I cannot store another pointer to 59 here. So in that result, what we do is, and this mechanism, what I'm showing you is known as a chaining. So what I'm doing is I am in the hash value, I'm keeping another value for 1, and these two ones are chained with each other. So let's say when I'm trying to search for 1, I first go to this, and I'm chaining them. So let's say if I'm trying to search for I'm trying to search for hash value 2, I do not find roll number 47. So what I'm going to do, I'm going to follow this link, I'm going to follow this chain, go to the next record and see whether the second roll number is present or not. So if I'm searching for 59, I first do 59 mod 3, whose value is 2. I go to 2 and I see hey, 2 is not pointing to 59, it is pointing to 47. So there is something problem here. That means a collision has occurred here. So what I'm going to do, I'm going to follow the chain that 2 has given, and I'm going to go to the next record of 2 in the hash table. And here I see, hey, you know what, 59 is present. So I'm going to go ahead and go to the 59. So these values which I'm seeing here, these are the overflowed values. The first 3 values that are there, those are the actual correct values. But after that, since your hash function is causing a lot of collision, because actually I've chosen a very bad hash function, like roll mod 3 is a very bad hash function. There will be a huge amount of collision. Every 3 records will be a collision. So that's why I'm creating a chaining mechanism where I've chained it to the next portion where the same value is stored. So this is how an hashing example works. Now, when you're doing external hashing, things get a little more complicated. Because see, one thing that I have done here is, say, for like almost for each and every record, I'm keeping an entry in the hash table, either an overflowed record or a direct record. But the problem that happens is when you're actually storing the data in physical memory, this table is huge. There can be millions and billions of records in this particular table, right? So your hash table is also going to get big. So it is impractical to store such kind of a hash table in the primary memory in the RAM. So you need to store the hash table also in the file header. That is, you need to store it in the physical disk only. So in that situation, we use something called external hashing, which is almost similar to that of internal hashing only, or rather the basic philosophy of generating a hash key is similar. But here, instead of pointing directly to the record, like here you see your hash table, you are pointing directly to the record. Instead of pointing directly to the record, you are pointing it to a bucket. And this bucket contains multiple blocks. And each block can have multiple records. So you're pointing to a bucket. Your hash value points to a bucket, and then that bucket contains multiple records. And one of the records in that particular bucket is what you are actually looking for. So here the hash function generates a bucket number and not the record pointer. So here how it works. So let's say you've got multiple buckets and you have got a hash function of k mod 2. And if you're hashing a value of 3012, that will go to bucket number 2. So any record whose key is 3012 will always reside in bucket number 2. Similarly, any record whose value is whose key value is 1000 is going to reside in bucket number 0. So this is how the bucket numbers are decided. And if you see how the bucket numbers to the actual record pointers work, so these are the buckets. So here I just showed one bucket, and now I'm double clicking on each bucket and I'm expanding that bucket. Each bucket contains multiple keys. Let's see, bucket number 0 contains key 1000, 2010, 45, 60, 71, 90. And each of this pointing to the actual. So this is the actual physical database. And each one of this is pointing to the actual record. Same thing is kind of happening here in bucket number 2 as well. So these are the keys which have been placed in bucket number 2. And these are the record pointers pointing to each of the buckets. So this is what is known by or meant as external hashing. Now, external hashing has got a problem. The problem with external hashing is that these bucket numbers, they are actually limited. The number of buckets are actually limited. So if there are too many number of buckets that gets created, then that causes a problem later on. So this is known as static hashing. So for solving that problem, we have got something known as extensible hashing, which I'm not going into it here again. But if you're interested into it, you can actually search for what exactly is extensible hashing and how do we solve the dynamicity. How do you solve the dynamic problem there? Before I go into the main topic, which is indexing, I would again like to go ahead and check whether there are any questions in the live chat. There aren't any questions in the live chat. All right, fine. Then we will go ahead and finish up with indexing. So indexing, again, the concept is pretty similar to that of hashing. That is, you're keeping a separate table, and in the separate table, you're actually creating an index key which is pointing to the original data record. However, this is using a different mechanism. It is not exactly using hashing mechanism. It is using some clustering format. It is using some non-clustering format and stuff like that. And you're not really generating a hash table. You're generating something called a B plus tree here. So again, like this is one of the places actually like when we are learning about data structures and algorithms, right? A lot of times, a lot of students come back and don't understand that all these data structures that we are learning, like graph trees and everything, where exactly are they used? So this is one of the places. Indexes in databases, in SQL databases, uses B plus tree to store the information. So this is one of the places where you can see a practical example of your data structures algorithm knowledge being put to test. Anyway, so indexing, as I said, the concept is pretty much similarly, it's pretty much similar. That is, all that you are doing is that you are creating some sort of an index key somewhere, and then that index key is pointing to the actual record. So whenever your SQL has to search for something, it is first going to go to the index table, search for the data there. If the data is, if it finds the data there, and searching in the index table is going to be very fast compared to searching in the main table. So it finds, if it finds the data in the index table, then it is going to go to the, it is going to follow the pointer, go to the record where it is the main table, and is going to give you back the result. So that's what indexing actually essentially does. Now, there are two types of indexes that you have. One is known as the clustered index, another is known as the non-clustered index. Clustered index, you can create only one. It is very fast, but you can create only one for each table. So if you've got one table, then you can only have one clustered index onto it. You can have multiple non-clustered index, but you can have clustered index, you can create only one. So what clustered index basically does is, it determines how the record in your table is actually going to be sorted. So if I take the example of the student table again, and I say I've got clustered indexing on the name, then it is going to sort the values, or it is going to sort the records that you have in the student table in ascending or descending order of their names. That is what clustered indexing actually does. It simply sorts it, nothing else. And now when you need to search something in the clustered index, it's very easy because the record is already sorted. So all it needs to do is a binary search, and then it is going to give you the record, and binary search is very fast. It's O of log n. So that is how clustered index increases your query speed. That is, it simply sorts it, and after it has sorted it, when you're trying to query for something, whether you're trying to query for a range or you're trying to query for a single value, it's a simple binary search that it is doing. And binary search being very fast, it's going to give you the record really fast. So that is what clustered index is all about. But the problem is, when you're storing the record, and this is actually by common sense itself, that when you're storing the records or storing the data in a particular table, you can store it in only one order, right? You can't store it in multiple orders. Like, I cannot say I'm going to store it in the order of roll numbers as well as in the order of the marks that each student has received. You cannot do that. That is not possible. So you have to store the records only by ordering it by one particular attribute. And since clustered index works on the concept of ordering, that is, it just maintains, or it just tells you under which order you need to store the information, you can have only one clustered index per table. You cannot have multiple clustered index. Next is the non-clustered index. So non-clustered index is the way how we saw hashing, how it works. And for here, the records in the data table doesn't need to be sorted. So what it does is, let's say you're creating a non-clustered index on something like, let's say, let me give you an example here probably. So I'm creating the cluster on the department ID, let's say. Sorry, I'm creating an index on the department ID, let's say. So what it is going to do, it is going to pick up all the unique department IDs that you have, keep it in a different table. We generally call it as the index table. And from the index table, it creates it maintains a pointer to the original table, or we know it as a data table. So in non-clustered index, you are actually creating two tables, an index table and a data table. And the index table is having pointers back to the data table. That is how non-clustered index actually works. And the data in the index table is always going to be sorted, because when I need to do range calculations and everything, that's the reason why data here needs to be sorted. But the data in the data table, that doesn't need to be sorted by the index column. So here you see department, it is not sorted by department. However, here in the actual table, or rather in the index table, here you can see the data has been sorted by the department. So if I need to find, hey, I need to find department 3, what I'm going to do, I'm going to first go into the index table, search for department 3, and here it is very fast. Here it is ordered, right? It's a binary search. It is automatically going to give me the results really fast. And then I'm going to check this record is this value, this data is pointing to how many records. So it is pointing to this value and this value. So roll number 2 and roll number 6. And here you can see roll number 2 and roll number 6, both of them are in the department number 3. So this is how non-clustered index works. So one big advantage, or rather disadvantage, that you can find with clustered indexes, advantage is that it doesn't require any extra space. See, all it is doing is, it is just determining how your data is going to be sorted in the table. So there you don't need to store any extra information for it. That's the reason why clustered indexes do not require any extra spaces. However, non-clustered indexes do require extra spaces, because we are actually storing an index table. So depending on how big your data table is and how diverse your data is on which you're actually creating the index, your index table size might also increase. So when you're creating indexing, your database size is also going to increase. And that's one of the major disadvantages that you have with something like a non-clustered index, or with indexing and in search actually, because indexing generally, it will increase your speeds and everything. Right? I'll see if there are any questions over the chat on indexing. All right, I did not see any questions on the chat. All right, that's fine. Moving on, so I'll not be due to the interest of time. We will not be going into how to create indexes and everything on in this video itself. So this is something which we'll be looking into the next video, where we'll be seeing how we can actually create an index and how we can drop an index and how data automatically gets sorted and everything on particular indexes. So those are things that we'll be doing it in the next session. But I would like to just talk a little bit about some of the tips and tricks when you're doing indexing. And once again, indexing is very important to everyone. It is not do not take that lightly, because indexing can do magic, especially if you're on SQL. You can have billions and billions of records, but if you have indexed your data properly, you get back results within fraction of seconds. And we have seen, and like in production workflows, I've seen that working. Like if you're putting indexes on the proper fields, it can speed up your query like mad. So those are things that you need to understand really properly. You need to understand how your business is going to actually work, and based on that, you should be creating your indexes properly. And again, if you're creating wrong indexes, that is, you have indexed the wrong values, then that can degrade the performance like nothing. So you need to be very careful when you're creating indexes. Like when database optimization comes, and if in the enterprise world, you have specified people. There are special people who are specified, or rather who are specialized in actually optimizing your database. So these are the people who have some extremely good idea about how indexing works and on which attributes and on columns you should actually be creating your indexes and stuff like that. So these so this is again a very lucrative you can say a position or a skill, you can say, that if you can optimize SQL databases really well. So a few things that you need to keep in mind when you're creating indexes is you need to understand how your business works. That's the very first thing. See, indexing or hashing, whatever it is, basically indexing only. Indexing is what is actually used. Indexing only works on the fields that you have indexed on. Like for example, here I have indexed on the department. So that's why when I'm trying to write a query where department is present, like let's say I've written a query, select star from students where department ID is equal to 3. That query will be awesome, because I'm trying to query on department ID and on department where you have actually created an index. However, what happens if I now try to create an index where I say select start from student where student name is equal to Pratik B? Here you don't have an index, right? You don't have an index created on name. So it is actually going to go to the main table and is going to search for all the records that is present here. So that query will be slow. So now when you're creating your indexes, you first need to understand you need to sit with your business experts, with your program managers and your users, and understand what type of queries will be executed on the database on this particular table. And you should be creating index only on those columns and not on everything else. So if you know that search by student name is not a very practical scenario, it's a very small scenario, only it will happen once or twice in a month and stuff like that, it is fine. You don't have to create that index, or you can create temporary index. When that searching will happen, you'll create that index at that time. But if you know that there will be a lot of queries done on the department ID, like there will be, let's say, complicated joins and stuff like that is going to happen on the department, it makes sense for you to create a non-clustered index on the department. Second thing is about clustered index. One thing, clustered index by default is always created on the primary key. And generally, whenever you're doing joins and everything, you do the join on a primary key and a foreign key. That's the reason why it makes sense in 90% of the cases to have the clustered index created on the primary key. No need to change it. However, there are certain situations, and I have faced those situations in my practical life as well, where the creating it on the primary key did not make any sense, because there were some other keys which were being used really well, and it was better to keep the table ordered in that order rather than in the primary key. So that's the reason why you can drop an index that is created by default on the primary key, and you can create a clustered index on a non-primary key as well. Now be aware of creating too many indexes, because the problem that happens with too many indexes is, see, that although your query speed will be fast, it will be very fast, because every table is now indexed. So whenever you're writing a where query, SQL is always going to check, okay, we are doing a where on this attribute, and this attribute I already have an index table, so let me go to the index table, fetch the data, and then I'll go to the record table, which will be very fast. However, the problem that is going to happen is, see, now or you can actually visualize this problem. Now if I have to enter a new student here, I don't only have to enter the data in the data table, in the actual student table. I also need to go ahead and modify the records that is present in the index table. So if it is a new department, I need to enter a new key here. If it is an old department, I need to update the pointers and add a new pointer here. So what I basically mean is, if you're not doing read operations on the table, if you're doing some write operations, you're writing a new data, you're modifying an existing data, you're deleting an extra data or something like that, you need to go back and do the same operation on the index table. And if you have 100 indexes created on a table, you need to do that operation 100 times. On each and every table, you need to do that operation. And until you finish all the operations in all the 100 tables, since your database is atomic in nature, that is, it supports the ACID transactions, your transaction will not be completed. So you need to wait for a long time. So your modification requests, your insert, delete, update, the speed of them will decrease with the number of indexes that you are creating. Now, if you're okay with that, if your business is okay with that, if your business is fine, if you're trying to enter a new student, I can wait for let's say 10 seconds, 15 seconds. We are good with it as long as you are giving them the query result in a few milliseconds. If your business is fine with it, good, go ahead and do that. That's not a problem. But however, be careful of it, because when you're inserting a record or deleting a record, that also attributes to the user experience. And if a user has to wait for let's say 30 seconds to insert a new record or delete a record or modify a small thing in a particular record, it is very frustrating for the user. So you need to have a good balance between the query and the insertion and the write speed. Query speed is obviously very important, but you should not go ahead and create indexes on each and every column that you find. That is going to cause issues later. And the last thing is non-clustered indexes requires extra space in the database, so keep that in mind. So again, if you're creating 100 indexes, that is 100 non-clustered indexes, you are creating 100 index tables. And for maintaining that 100 index tables, you need to have space. So if you have, let's say, 1 terabyte of data, your indexes itself might take some few GBs of data out there. So you need to be very careful about that as well, about creating too many indexes. So yeah, so those are the things that you must keep in mind when you are actually working with indexes and when you're trying to create index and everything. Before I end, once again, I'm going to take a look into the live chat, which is, we don't have any questions there, which is fine. So if you have any questions, once again, please put it in the comment section, or if you have already registered for the course from Newton School, you can post the question directly on Newton School's website. So I think we will call it a day today. Thank you everyone for joining the session. I hope that you folks got to learn something. So in the next session, we will be doing some practicalities on indexes, and then we'll also be trying to create a very small application of where we will actually connect your application with a database. So we'll be creating a small Java application, and then we'll have a database hosted somewhere over the cloud, and we'll connect that database to your Java application. So that is going to give you some taste of that, how you can do actual real world application development using databases. So that's another interesting thing that's coming up in the next video. So stay tuned for that. So thank you once more, everyone, and have a nice day. And we shall call it a day today. Thank you.